Good morning, everyone. The first talk of today's morning session and only session today is by Professor Shinsuke Iwao from Keio University. We'll talk about the relativistic Toda lattice and quantum K-Schubert classes of Lag manifolds.
Yeah, thank you for the introduction. I'd like to say thank you to the organizers for giving me a great opportunity to give a talk in this nice conference. So in this talk, I would like to explain how techniques from classical integrable systems can be applied to the modern geometry. The title of my talk is the Relativistic Toda Lattice and Quantum K-Schubert Classes of Lag Manifolds. This talk is based on the joint work with Takeshi Ikeda from Waseda University, Satoshi Naito from Institute of Science Tokyo, and Kohei Yamaguchi from Nagoya University. Okay. This talk is based on the content of this paper. Currently, this is in preparation. Okay. The topic of my talk is quantum K-theory. Quantum K-theory is a ring that describes some structure of algebraic variety. Quantum K-theory of algebraic variety was introduced by Gibb et al. This is some K-theoretic counterpart of the quantum cohomology of algebraic variety. It is a kind of algebraic invariant that captures the structure of the set of all vector bundles of the variety. So, in general, if you given a algebraic variety X, you can construct some algebraic invariants in various ways. I think it is most famous. I think the cohomology is most famous algebraic invariant of algebraic variety. Generalizing that, you can obtain quantum cohomology K-theory or quantum K-theory. They are all algebraic invariants of algebraic variety X. Cohomology ring describes the structure of subvarieties of X and with intersection numbers. Quantum cohomology describes the structure of subvarieties with Gromov-Witten invariant. K-theory describes the structure of X, the structure of vector bundles over X with tensor product. And quantum K-theory is describes a structure of vector bundles over X with K-theoretic Gromov-Witten invariant. They have their own characters and they have very important and interesting things. But in general, it is very difficult. It is very difficult to calculate these rings and determines their structures. So let me show a simplest example. If X is projective line, this is most simple projective variety. If X is projective line, you can calculate these four rings as follows. Cohomology is generated by a class of a point. And the relation x cubed equals x squared, sorry. The relation x squared equals 0 means that 2 points in general position does not have intersection. quantum cohomology is a quantum generalization of cohomology. So you can find the quantum cohomology of complex projective line is expressed like that. So this is similar to cohomology, but deformed by quantum parameter Q. If you put Q equals 0, you can recover the usual cohomology. The case theory of projective line is expressed as follows, like that. X is some special line boundary. The relation x squared equals 0 means the tensor product of x and x is isomorphic to zero-dimensional trivial boundary. And you can quantize the case theory like that. Similar to the quantum cohomology, if you put Q equals 0, you can recover usual case theory. So I show a more complicated example. If X is a complex project space of dimension n, you can calculate these 4 rings: cohomology, quantum cohomology, case theory, and quantum case theory. So in this case, cohomology and case theory are isomorphic, but in general, they are not isomorphic. For example, if X is Grassmannian, that parameterizes all two-dimensional spaces of four-dimensional complex vector space. The cohomology and case theory are isomorphic in this case, but quantum cohomology and quantum case theory are not isomorphic. Also, you can recover usual rings by putting Q equals 0 to quantum things. So I don't explain how to calculate these rings. If you are interested in this calculation, see, for example, this lecture note. This is a very good note, so you can recover this calculation from this. Okay. In this talk, I want to go further. So projective line, projective space, Grassmannians. So the next simplest projective variety, I think, is Frag variety. In this talk, we consider the quantum case theory of Frag manifold. So that parameterizes all sequence of sub vector spaces of n-dimensional complex vector space. So it has been known, it has been shown that the structure of quantum case theory of Frag variety, Frag manifold, is deeply related to the some difference equation from classical interval systems. Using this fact, various important results, for example, the structure constant or QK or something like that can be calculated using this fact. So my goal is to calculate more concretely or more explicit formula, to obtain more explicit formulas using classical integrable methods. For this, we consider the following 3 rings. One is a coordinate ring of the phase space of the relativistic Toda lattice with a special initial value. So I don't explain what is a special initial value because I can remove this condition later. So I don't explain, go further here. Next one is quantum case theory of Frag manifolds. I explained earlier. That is the ring defined by introducing some product, a quantized product into the K3. And the last one is the K-homology ring of the Ramanujan. I'm sorry, I don't explain here what is the K-homology ring, but I will show later the explicit representation of this ring. So I cannot explain here, but we have an explicit representation as a ring later. So there is 3 rings that are isomorphic. It is known that they are isomorphic after some appropriate localization that has a few inverse elements to the ring. So we want to go to this side. We want to go to this side starting from this side. We want to connect these 2 rings. Number 2, there are 3 isomorphisms. Number 2 is something like highway, something like modern geometry highway is 2. This is established by these authors. The map 2 is said K-Peterson isomorphism. So the K-Peterson isomorphism is something mysterious because it connects the quantum K-theory of usual flag manifold to usual K homology of Ramanujan. This is a very mysterious isomorphism. So there is a slogan, quantum equals affine. So it is mysterious mathematical fact, but there is a slogan, quantum equals affine. So number 2 is something like a highway, but I want to go to climb this classical integrable mountain. So this is so you can think this is some not good way to go there from this side, but as the classical integral systems has very much concrete or explicit formulas and interesting features, algebraic features. So it is not bad to go up a route from here to here. So looking closely to the upper square, you can divide this red square to 2 parts because the phase space of classical integral system has 2 canonical expressions. One is the right-hand side one. One is a lax presentation of the integrable system. Another one is a presentation using canonical variables, action variables and angle variables. So the connection of these 2 expressions are realized by constant type matrix decomposition method. So you can go up to the quantum K homology, quantum K theory to the coordinate ring of phase space. And using constant type method, you can go the world of action and angle variables. And later, these 2 parameters can be connected to the K homology ring of Ramanujan. This is a total picture of our strategy. So we need to go up using route 1 and go to right using following route 4 and down following the root 3. Okay. So these isomorphisms demonstrate how techniques such as the matrix solutions or background transformations in classical interval systems can be applied in modern geometric research. Okay, before proceeding, I have to a bit generalize the situation. Because frag variety has a torus action, there is a torus equivariant quantum K theory with torus action. So this is an equivariant generalization of our topics. So you may think it is more complicated, more complex than the non-equivariant case. But for me, or for integrable systems, it is more natural. Equivariant generalization is more natural than non-equivariant version. Because, please see the line one. Equivariant K theory has equivariant parameters. If you put equivariant parameters to some special value, you can recover usual quantum K theory. So equivalent quantum K theory is a equivalent generalization. Non-equivariant case, I must consider a coordinate ring of relativistic Toda lattice with a special initial value. But after generalization, I can consider relativistic Toda lattice with a general initial value. For me, general initial value is more natural. Therefore, equivariant K theory is more natural for me than non-equivariant one. So this is a natural and good generalization of our topics. Okay. One note is that our theme is regarded as a K-theoretic generalization of the cohomology, quantum cohomology theory. It is well known that a coordinate ring of the phase space of the Toda lattice is isomorphic to the equivariant quantum cohomology of frag manifolds. So from this perspective, relativistic Toda lattice can be seen as a K-theoretic generalization of the Toda lattice. Okay. Okay, I will explain the more detail. So, however, I cannot do geometry here. So, this is my definition of quantum K theory. I don't define quantum K theory by geometry. This is my definition of quantum K theory. This is defined by generators and relations. Let us consider the T. Let T be the maximal torus, and RT is a representation ring of T. There is a EA1 and EAI. If you put AN to 0, you can recover usual quantum K theory. So this is proved by Maeno, Naito, Sagaki that quantum equivariant quantum K theory of frag variety is represented like that. There are Q, T, and EAI are generators, and there are relations. So F is a polynomial of Z and Q. This is an important thing. I will return this polynomial later. Yes?
REI, there are symmetric polynomial in variables. So
No.
What is EI?
No symmetry.
EI.
EI. No. Just Euler number. Just just Napier number. Napier's number. Just E number. Just.
So EI and EI and the second line from the bottom. EI.
Okay. Yes. This is elementary symmetry problem.
Okay.
Yeah.
Thank you.
Sorry, and what is upper QJ in your bottom line?
Upper QJ.
Well, uppercase Q, yeah, big Q. No, just a little to the right. In your bottom line, yes.
So this one?
Yes.
This is a Novikov variable. This is a quantum variable. And if you put Q equals 0, you can recover usual case theory. Sorry, this one. Q equals a set of Q1 to Qn minus 1.
Right. Sorry, thank you. Mm-hmm.
Okay. So this theorem says that quantum K theory can be expressed as by generators and relations. And T equivariant K homology ring can be expressed as by using polynomials. Let Y be infinitely many independent variables, and lambda be the ring of symmetric functions. So then there exists an inclusion that emerges to from inclusion from T equivariant K homology ring to the ring of symmetric functions tensored by some ring. So you can any element of T equivariant K homology ring can be seen as a symmetric polynomial, a symmetric function in Y. This is an explicit presentation of the K rings. Okay, so we have explicit representation of these things, and there exists some good isomorphism between them. So this is called K-Peterson isomorphism. The structure of K-Peterson isomorphism is described by some combinatorial way. There is a general concept considering about flag varieties. Flag varieties or affine Grassmannians contain a family of distinguished subvarieties called Schubert varieties. And Schubert varieties are parameterized by some combinatorial object. For example, a while group or affine while group or partitions or some generalization of partitions. In our case, quantum K theory of flag variety, in this ring, there exists a family of polynomials that represent Schubert varieties. This polynomial is called a quantum double-Grothendieck polynomial. Z and Q are variables of polynomials, and W is an element of symmetric group. So Schubert varieties in quantum K theory is parameterized by symmetric group. On the other hand, in equivariant K homology, there exists a family of polynomials like that that represent Schubert varieties in affine Grassmannian. This polynomial is called a K-theoretic double K-Schubert function. Y and B is a variables of polynomial, and this is parameterized by X. X is an element of a set of minimum coset representatives of this set. W is while group and W hat is affine group. So in quantum K-theory and in quantum homology, everything is combinatorial. You can explain everything in combinatorial way. The K-Peterson isomorphism also explained by combinatorial, in a combinatorial way. So there is a theorem that says that there exists a ring home isomorphism. This is a K-theoretic Peterson isomorphism. And LOC means some localization. So satisfying this equation may be complex, but this is very combinatorial and not complex. So if you want to calculate image or inverse image of phi, only thing you have to do is decomposition of x. If you decompose x to the product, decompose into product of W and T mu, you can recover the inverse image of the K-Peterson isomorphism. So everything is combinatorial. Okay, this is an K-Peterson isomorphism. I want to climb this mountain and go right-hand side and down. First step is the Rux matrix presentation. So this is the Rux matrix presentation of the relativistic Toda lattice discovered by Rinat. The matrix is discovered by Solis in 1994. So if you define these two matrices M and N and define L equal to that like that, the relativistic Toda lattice can be expressed as like such Lux 4. So this theorem is shown by Ikeda and Milo and me. The characteristic polynomial of L is expanded like that, and the coefficient of the characteristic polynomial is the same as polynomial f that is explained before. F is sorry, I returned back. Here. This polynomial f. This polynomial f. This defines the relation of T equivalent quantum K theory. So the theorem says that you can recover the structure constant of quantum K theory by using Lux matrix of relativistic Toda equation. So there is very strong relation with quantum geometry and classical integral systems. And the defining equation, this one, the defining equation of I, it says that the spectrum of the Lux matrix is this set. So there is a very natural interpretation in terms of classical integral systems. So I can go upstairs. Next, go to right, following the constant type method. So it is something like well-known technique. Let A be the matrix like that. Obviously, the spectrum is of A. It's A minus A i's and E minus A twos and like that. And let Z be a set of matrices that commute with A. Then there exists a birational map from the phase space of relativistic Toda equation to the set of n variables, set of n variable and one matrix, such that the flow of our relativistic Toda lattice is mapped to the system. This is linearization of the relativistic Toda equation. After the linearization, the flow of the integrable system can be linearized and easy to solve. Okay, constant type method for relativistic Toda equation is as follows. Let C be the companion matrix of A. Okay. Then Z is decomposed as follows. U is lower unipotent upper triangular and R is lower triangular. If you decompose this matrix like that, you can recover Lax matrix like that. This is a constant type argument that solves classical integral system. So you can go to the right-hand side. Next, we want to go down here, but before proceeding, we have to consider the action of symmetric groups to these four rings. The action is very simple. There is a natural SN action that permutes the spectrum. This is just permutation, very simple. But, however, the permutation is simple for this one and this ring. But because matrix A can be changed by the action of SN, the action variables and angle variables both can be changed by the SN action. So I have to be careful. So SN action of the centralized space, it's something a bit complicated. So it's defined by the matrix conjugation like that, and so with this matrix M. You can prove that SIZ, this map defines the action of Sn on the centralized space. Okay, so I get an Sn action on four rings. Then I can define some operators acting on all rings, all four rings. This is a demerger operator. On these four rings, the following demerger operators can act because Sn acts on all four rings. These operators can be defined on the four rings. Okay, it is known that the quantum double Grothendieck polynomials can be generated by demerger operator as follows. This relation, seeing this relation, we can know that every quantum double Grothendieck polynomial can be obtained from Grothendieck polynomials associated with longest element and finite many times action of demerger operator. So this is a result. There exists a certain operator. Sorry. At this stage, I have only n minus one demerger operators, d1, d2, and dn minus one. However, there is a good theorem that there exists a new certain operator D0 that acts on the four rings such that D0, D1 to Dn1 generates some, satisfies some good algebraic condition. They generate the Nilheke algebra of type A. And on Grothendieck polynomials, the action of the major operators can be expressed as follows, very explicit formula. You can get very explicit and combinatorial formula. Also, the major operator acts on K homology side. The action of the major operators can be calculated also very explicit and combinatorial manner. It is very good result about the quantum K-theoretic Schubert calculus. Okay, so finally I get the major operators acting on these four rings, and using the major operator, you can explain every structure of double Grothendieck polynomials and double K Schur polynomial. So you can get this entirely this diagram. So the merit of climbing this mountain is one of the merits is that there is very explicit formula and there are many useful extra variables. So in this case, we are considering 2n dimension space in general. For example, there are n spectrum and n action variables and n angle variables. So there is an 2n dimensional system. However, using centralizer representation, you can obtain very, very much variables. You can obtain much more variables, much more extra variables that can be used to calculate something explicitly. Okay. So this is a theorem. This theorem says that you can express Schubert subvariety in K homology, quantum K homology by using explicit determinantal formula. This determinantal formula can be obtained by matrix decomposition and comparing coefficients or something like that explicit. So if X is K small means that X is sufficiently small. I don't explain here, but if X is sufficiently small, we have the Jacobi-Trudi type determinantal formula for the K-theoretic double K-Schur function. This I don't describe it explicitly here because the matrix is very large, and so. But you can obtain a certain square matrix whose elements are simple function of S, Z, and E, whose determinant equals to the some characteristic, some important polynomial in the quantum K theory. So as far as I know, our determinant formula is new even for the non-equivariant case. Okay, finally, you can go down right-hand side by comparing using our new determinant formula. Okay, so as a conclusion, we constructed the alternate way to define K-Peterson isomorphism using integrable system, relativistic Toda Lattice. And we establish the new Jacobi-Trulli type formula for K-theoretic double K-Schubert function when K is not so sufficiently small. And we have more results. For example, factorization formula or explicit presentation for some non-K small but typical polynomial, or the relation to background transformation and geometric sum operators. Okay, okay, I stop here. Thank you.
We have time for questions. May I ask a question? So, as you mentioned, the Toda lattice can be used to describe quantum cohomology of flag variety, and relativistic Toda for quantum K-theory. And you also mentioned Backlund-Darboux transformation, and there is a Backlund-Darboux transformation that sends usual Toda to relativistic Toda. So if you go to the other side, does it give you some meaningful map between this homology rings? Or?
That should be very interesting. At this stage, I don't know, but it should be interesting.
And one more question. This determinants that you mentioned but didn't show, are they related in any way to Toda system tau functions maybe? Or?
Yes, tau function. So the K-theoretic double Schur function associated with some special form, rectangular, is equal to the tau function of relativistic Toda lattice.
Sasha.
Mish, first I have a comment to your question. So I think, well, when you said usual Toda versus relativistic Toda, here relativistic is the multiplicative one, it's the trigonometric one, relativistic in this sense.
Sorry.
So you mentioned in your question, you mentioned usual Toda versus relativistic Toda. But here relativistic is not in the sense of choosing a particular double Brouwer cell, but in the sense of trigonometric version of this, right?
Sorry.
But yeah, anyway, sorry, and in your diagram with four maps. So do you understand it right that the top horizontal map is basically it's a spectral transform for the Toda lattice?
Sorry, spectral transform is
so you take Toda Hamiltonians on the left and you diagonalize them, and you get your variables e to the aj. Is that correct?
Spectral. The way to left to right is spectral transformation, I think. So, what is your question? Sorry.
No, yeah, okay. I just want to confirm that. Okay, thanks.
Yes, Ray, please.
I'd like to understand the constant type method more precisely. So could you show the slide to define capital Z? So you fix A, matrix A, and define the commuting the set of this one. Yes,
This one,
and yes. Then so what the dimension of Z?
N. So because from the condition that Z commutes with A.
Yes.
A. So non-diagonal element is a function of diagonal elements.
Yes, and as far as I remember, you added the condition for A from A1 to AN.
Right.
Yeah. So
right.
what? Yeah.
N minus 1. Yes, yes.
So actually, the dimension of the phase space is what? 2n minus 2.
Yes, yes, 2n minus 2, yeah. Yes.
I see. So I'm confusing a little bit now. So you define the time from t1 to tn
Yes.
by using this,
Yes.
and
Oh,
moreover, you define. What happened there?
Yes, sorry. I have to some condition. I have to make some condition that the product of these values equal to 1. So there is a error type. This is typo. Sorry. So this is an n minus 2 dimensional space.
Yes. And what happened to the time ti with that condition?
There is a there is a relation that that trace equals to 0. So there is a condition.
Some relation.
There is a Kelly-Hamilton formula for square matrix.
Yes.
So the condition that the trace equals to 0.
I see. So it gives some independency for time.
Yes.
I see. Nice. And so, does this condition affect the action of the de Mazur operator? So
No.
Maybe it's a very bad question.
No, because they are homogeneous. So you can multiply same constant to every parameter. So there's no difference.
I see. Then, I'm sorry. So can I continue? So you mentioned that in the last stage of your talk,
yes.
That there is additional structure for Z, the capital Z. So in the off-diagonal part, in the upper part of Z, you used Zij to give something. Maybe much later, Zij or something you wrote. Yes. So I'd like to know about extra variables more precisely.
In principle, every off-diagonal elements is expressed as a rational function of diagonal elements.
Yes.
But Zij itself is have good behavior under the de Mazur operator. So if you don't have off-diagonal elements, it should be very complicated formula. But if using off-diagonal elements, you can reduce more complicated formula to more easy formula.
I see.
These extra variables is very good for calculations.
I see. So I see. I understand. Thank you.
Any other questions? If not, let us thank Iwao-san again. And the next talk is at 10:30.